Related rates can be used to find the rate of change for a number of things that you can observe in the real world. For example, suppose we have someone standing 30 feet from a drone's launching point. We can use the distance between the person and the drone's launching point, the rate at which the drone's height is increasing, and the height of the drone itself, to determine how fast the distance between the person and the drone is changing when the drone is at a certain height. And we're actually gonna do just that. But wait! Related rates can become difficult unless you follow 8 simple steps. Don't worry about memorizing them, you'll eventually commit them to muscle memory. Step 1. Always draw a picture. Label all sides, quantities, and rates of change. Step 2. State what you're given in terms of a rate. Step 3. State what you're trying to find. Step 4. Relate the quantities. Find an equation that ties all your variables together. If it's an area problem, use an area equation. If it's a right triangle, use the Pythagorean theorem or trig formulas. And side note, if your function is an equation of 2 variables, write a secondary equation and solve for one of the variables to get your related rates equation in terms of a single variable. Step 5. Use implicit differentiation to take the derivative of both sides of your related rates equation with respect to time. Step 6. Plug in known information and solve for the variable that you're trying to find. Step 7. Always answer in a complete sentence, or else it won't be counted. And finally, step 8. Remember that you're awesome. Now that we know the 8 steps to solving any related rates problem, we can get to business. Let's look at the drone problem in more detail, using some really cool drone footage in the background. So here we have Zach standing about 30 feet from a drone. The drone is rising at a rate of 10 feet per second. At what rate is the distance between Zach and the drone increasing when the drone is 400 feet up? State your answer in a complete sentence, and please don't forget to use the appropriate units. Let's start by drawing a picture. Zach is 30 feet from the drone's launching point. H is the drone's height, and X is the distance between Zach and the drone. Now we state the given rates of change. We know that the drone is increasing in height by a rate of 10 feet per second. So dHdt is 10 feet per second. We want to find the change in x over time, or dx dt, when the drone is 400 feet in the air. We can relate all of our variables using the Pythagorean theorem. C squared equals a squared plus b squared. Now we derive the equation. Keep in mind, we're deriving everything with respect to time. So we multiply each derivative by the derivative with respect to time, or d variable over dt. Now we plug in our known information. In this case, we're going to have to solve for x. We can do so using the Pythagorean theorem. We find out that x equals 401.123. Now we can plug that in and solve for dx dt. As you can see, our answer turns out to be 9.972 feet per second. But you're not done until you state your answer in a complete sentence with the appropriate units. We can say that the distance between Zach and the drone is increasing at a rate of 9.972 feet per second when the drone is 400 feet in the air. Robert wears jorts. Now try finding the rate of change for the angle of elevation, or theta. Pause and try this problem on your own, and then play to see our answer. We already have the picture and the rates of change stated, and we have stated what we want to find, d theta dt when h is 400. We're going to use tangent of theta to have an equation with all of our variables. Then we derive that equation to get secant squared theta d theta dt equals dh dt times 1/30th. Remember, secant squared theta is just 1 over cosine squared theta, because secant is 1 over cosine. We can multiply both sides by cosine squared theta to isolate d theta dt. Now, all we do is plug in our known information and solve for d theta dt. Remember, cosine is adjacent over hypotenuse. Adjacent in this case is 30, and the hypotenuse, as we saw from using the Pythagorean theorem in the previous problem, is 401.123. Our answer is 0.002 radians per second, rounded to the third decimal place. Once again, state your answer in a complete sentence. We can say that the angle of elevation is changing at a rate of 0.002 radians per second when the drone is 400 feet in the air. In this video, you learned the 8 steps to solving any related weights problem, and you had the opportunity to observe those steps in action and to practice them yourselves. Feel free to rewatch the video or even leave comments if you have any questions, and as always, thanks for watching.